Okay, Bismillah ar-Rahman ar-Rahim. Let me now continue in this video. We wanted to do worksheet number 2, and we wanted to do questions, the new questions, the new added questions, which is question 4, I think 5, 6, 7, and so forth. Okay, so let me start with question number 4, which is somewhat straightforward and easy. So this question here, this question here is saying that you have two infinite sheets of charge and separated by 10 centimeters as shown in the figure, and then they gave you the surface charge distribution for each one of them. They're a little bit different, so these are not parallel plate capacitor. Don't be fooled by that. These are not parallel plate capacitor. One of them is 3 microcoulomb and one of them is minus 5 microcoulomb, and he wants you to find the electric field at point P 6 centimeters to the left of sheet 1 and then 6 centimeters to the right of sheet 1. Okay, let's start here. So we already did in previous. Okay, let me just adjust this a little bit. Yeah. Okay, so already done in quiz 2, quiz number 2. We found that the electric field near a sheet like this, if it is positive, right? If it is positive, then the electric field is directed this way, and it's equal to sigma over epsilon. Okay, and if it is negative, and of course it's directed this way, okay, same thing. If it is negative, if the sheet is negative, then the field is directed this way. Okay, this is the electric field. All of these guys are the electric field, except now they are they are different because sigma is where am I? Here. So sigma, this is negative sigma, and this is positive sigma. Okay, so the electric field everywhere it's equal to this position, is equal to this value. So when I am 6 centimeters here, right, when I'm at this point here, okay, now the distance does not come into effect because I'm considering these as infinite plates, and that means I'm close to the sheets. So the distance is not relevant. I'm going to treat them as an infinite sheet. That means the electric field for everything, everywhere, is equal to this value. So at this point here, I have the electric field. Let's call this the positive. Electric field positive is equal to sigma positive, which is sigma positive is equal to 3 microcoulombs over epsilon. Okay, and sigma negative here, which is in this case sigma negative. Remember, it's moved this way. So that's my the negative electric field due to the negative plate is this one, is equal to minus 5 microcoulomb over epsilon. So you add these two, you get minus 2. So E net at this point minus 2 microcoulombs over epsilon, and it is remember this is so it's directed to the I hat because this is bigger than the other one. Okay, now in the point here, remember here, one of them is directed towards this way. So the positive one is directed in the negative direction, and the negative one is directed in the positive direction. In fact, this is positive. So the direction will be of the electric field at this point here is directed this way. Okay. Now, for the negative plate, for this point here, both electric fields are directed along the I hat direction. So they add. So E positive is still equal to 3 microcoulombs per over epsilon, and the E negative is also equal to 5 microcoulombs over epsilon. Both of them directed this direction, so they add. When you add them, E net will be 8 microcoulombs over epsilon, and that's it. Okay, and that's the solution for this problem. Okay, that's question number 4. Okay, let's move on to question number 5. Okay, so what's question number 5 saying? Question number 5 says, okay, let me read that here. Question number 5. Okay, question number 5, it says that you have a charge Q that is distributed over a wire of radius A as shown in the figure. What is the electric field at the center? And then he wants you to plot the electric field, what's the electric field at the center as a function of theta, and then he wants you to plot it for an angle from 0 to 180 degrees. Okay, so what do I have? I have a wire that is bent like this, and somewhere here I have the radius R, and I wanted to find the electric field at this point. Okay, now let me notice the following. Let me just I need another color. I don't have it here. Okay, here we go. Okay, let me do the following. So obviously I'm going to do this using or by cutting this into small dq. So this will be my dq. Okay, and then I'm going to calculate the electric field due to this dq, and then integrate over the theta he gave me. So my theta will be from here to here. That's my theta that I'm going to integrate over. So let's start with the definition. The definition of the electric field, E, is defined as K, and then integrate dq, right? And of course dq over r squared r hat. Okay, my r hat, this is my r, and my r hat for this specific one will be this little vector that is over there. Okay, now let me, before I go any further, r, this distance here from from dq, the infinitesimal charge distribution to the center, is simply the radius r. So this is not a problem. So it just can come out k over r squared because it's constant, and then I have a dq r hat. Okay, let me notice we need to look at the symmetry here now. For every one of these guys, there is another one here, which is going to give me the same thing. Going to give me the electric field this way, right? The electric field this way. So what does that mean? That means the y, the EY will always cancel, and I have only EX. So the electric field that I'm going to calculate due to this arc is simply EX. So my electric field now, EY will be equal to 0, and EX will be equal to K over R squared dq cosine theta. Okay, because the X component is, if I take this angle to be theta, then it's cosine theta. All right, so that's what I need to integrate. All right, let me grab another piece sheet here. Clean sheet, and then see how we are going to do this integration. Okay, so far I have E along the x direction, just k of course over r squared is equal to dq cosine theta. The question is, what is dq? Now remember, q for a wire is equal to lambda times L. dq, an infinitesimal part of that, is simply d, in this case s. S is the arc. Okay, s is the arc, and the arc s is defined as r theta. So my ds will be r, because it's constant, d theta. So therefore my dq will be equal to lambda r d theta. Okay, let me put that in here. So that will be equal to k over r squared, and then I have a lambda r, and I have a cosine theta d theta. Okay, of course one of these guys will go with that, and then I have a k lambda over r, which is constant, some constant value, and of course the cosine is simply the sine, the integral sine theta, and of course from theta 0, from initial theta to final theta. But as a function of theta, the electric field as a function of theta is equal to k lambda over r sine theta. That's the answer to the first part. Okay, let me just put this over here, because in the second part, what he wants me to do, he wants me to show him or sketch the electric field as a function of theta. So if I sketch here the electric field, okay, this is on the vertical axis my electric field, on the horizontal axis that's my theta, because that's now the electric field. As you can see here, I'm just going to leave it over here now. The electric field is as a function of theta 0. Now we know the sine and cosine. It will, because it's a sine, it will start from 0, and then it will go something like this. So if I take when theta is equal to 0, I have a 0. When theta is equal to pi over 2, then I'm going to get sine theta is equal to 1, and this number here is k lambda over r. Okay, and when theta is equal to pi, I'm going to go back to 0, and when theta is equal to 3 pi over 2, so this is pi, this is 3 pi over 2, I'm going to get a minus that, which is somewhere here, minus k lambda over r, and then when I come back to 2 pi, I'm going to go back to 0. So the function that I get for the electric field is somewhat, it's a sinusoidal function that looks like that. Okay, this is pi, and that's the answer to this question here. All right, that's the answer to question number is it 5? 6. No, 5. That's the answer to question number 5. Let me do question number 6, which, as you can see, basically, I think this is solved somewhere else. I remember doing this before. So what does this question say? It says that you have a non-conducting sphere of radius 6 centimeters, has a uniform volume charge density that is equal to that much. What's the total charge of the sphere? And then he wants you to find the electric field at distances kada kada kada, and then he wants you to plot the electric field as a function of the distance away. Okay, first of all, this is a sphere, okay, and he gave me the radius, and he gave me the volume charge distribution. So that means I can calculate Q, which is equal to rho times V. Rho is given. This is the first question was the total Q of the sphere is 450 times 10 to the minus 9, because it's in nanocoulombs per meter cube. That means I have to multiply by the volume for third pi, and R is equal to 0.06 cubed, and that should give me, this is meter cubed and this is coulomb per meter cube, so that should give me coulomb, and this is the total charge. Now the second question, part B, so this is part A. Part B, he wants you to calculate the electric field. This is a non-conducting sphere, so he wants you to calculate the electric field at some, remember, anything below 6 is inside the sphere, because the radius is equal to 6 centimeters. So any value that is less than 6, that means you're inside the sphere. Okay, and anything outside greater than 6, you're outside the sphere. Okay, now we've calculated this in class. We've calculated, and you should go back to that. You should go back to that. We've calculated the electric field for a solid sphere inside the sphere and outside the sphere. So we've calculated that inside the sphere when R is less than big R, right? And outside the sphere when R is greater than R. And R, in this case, small r, is the Gaussian surface, is the imaginary or the arbitrary Gaussian surface that we select. So if we look here, 2 centimeters, that means I have to apply this one. Remember, my R in this case is 2, and my big R is fixed, which is equal to 6 centimeters. Okay? Or you can, of course, you have to work in meters, so this will be 0.6 meters, and this will be 0.0 meters. So you have, for the first one, you have to apply this equation, where it's the electric field is equal to KQ divided by 4 pi epsilon, and then you have an R over R cubed. Okay? The second one, 5.9, again, that is less than 6, so you have to apply this. And for the third one, you have to apply this, and for the the fourth one, you have to apply this. Okay, so I think that's just straightforward. You just have to calculate the numbers, and then you plot on a nice graph. You plot the electric field as a function of. I don't have the numbers with me, but you have to sort of calculate the electric field. The electric field as a function of R. So for R values is equal to 2 centimeter, in centimeter. Okay, 2 centimeters, 5 or 6 and so forth, and then you there actually should really, this is too full, yeah, okay, and then you should do that. So this should really be 1 2 or 2 4 6 8 so forth, okay, and then the electric field over there, the values, and you get you know what you're going to get. Inside anything below 6, you're going to get something like this, right, a straight line, and anything after after 6, you're going to get something like that. That's what the overall value should look like. Okay, so I'll stop here, and then I'll check if just to make the video short, and then I'll check with the other problems later on. Thank you very much. See you.